in the 40s to be used as nonstick coatings, especially on things like pans and some industrial metals like bearings and things like that. The two most frequently used PFAS compounds were perfluorooctanoic, barely say that, perfluorooctanoic acid, PFOA, and perfluorooctane sulfonate, PFOS. And so those are the two you probably hear about most often, PFOA, PFOS. And they were manufactured for a really long time and then finally discontinued in 2002, 2003 time period. They're no longer manufactured, but now we have what folks might refer to, you might see this in the literature, as next generation PFAS compounds. Basically, the folks who make these compounds, once they realize that one has been studied and is having negative effects, they change a small aspect of the chemistry, its shape, its size, and then they call it something else. And so these next generation compounds are also in our environment, but not as high because they haven't been, or not as high concentrations because they haven't been used as long as PFOA and PFOS. Next slide. What are the PFAS compounds used for? So we use them in our homes all over the place. Many of us have used nonstick pans for years. I finally threw mine out just recently, but if you had a Tefal pan or any sort of like Teflon nonstick pan, those are PFAS compounds that make the nonstick component. Stain-resistant carpets, you see the picture here. If you go to buy a carpet these days, they'll say, oh, do you want this stain-resistant? So if you spill a glass of wine, or you can make fabric stain-resistant, like for your couches. If you have kids, they'll tout that as a selling point. And so they're also in our clothes as well. For safety reasons, they're in firefighting foams. So a lot of fire stations have them. Even if they're discontinued, I've heard a rumor that some just pour them straight down the drain. So they're getting into our septic systems from disposal at fire stations. And they're also used at airports. So whether they're a military airport or a regional airport, they're used as firefighting foam in case there's a fire at an aircraft. And also the PFAS are used, as I said before, to make metals smoother. And so they're used in aerospace and automotive and electronics and military applications, all things to make machinery work a little bit smoother.
I'm just going to jump in
sure.
quickly. I forgot to mention this in the beginning, but this is a really informal atmosphere here. So if anybody has questions as we go along, there's a lot of content covered here. Just feel free to speak up and chime in. It'd actually be better to not do it by the chat box because we're hosting on my screen. So it would be very disruptive for me to have the chat box open while I'm screen sharing. So really just unmute yourself and speak up if you have any questions or need to go over something again.
Right, thank you. A lot of chemical companies make PFAS compounds. The first, one of the biggest popular ones was DuPont, which is now called Chemours. They made Teflon for the pans and things like that and for industrial coatings. 3M is another large producer of PFAS. They make the Scotchgard thing that you can spray on your couches or on your rugs. They also make sticky notes. I'll note that when Mark Smith from MassDEP advised us, the group that studies the outfall about PFAS compounds, he said that he told his daughter not to use sticky compounds, so I'm sorry, sticky notes, because of the risk of PFAS getting on your fingers from the stickiness that makes these things work so well. The large international company BASF uses PFAS in varnish and paints and in container coatings. And then lastly, for those of us who like outdoor gear, Gore and Associates, Gore-Tex, the laminates that make clothing waterproof or shoes waterproof. Gore-Tex is a PFAS sheet. In fact, they made dental floss for a while, the Glide dental floss. Gore-Tex was making it. They sold the patent to Glide. Glide floss is PFAS. So if you're flossing with that thin floss that works really well, you're putting PFAS right into your mouth, which is unfortunate because it worked really well. Next slide. So these, as I said before, these substances, there's a lot of them. There's thousands, and they're divided into different groups based upon the length of the compound and then something called the functional group. So if you look at the picture on the right, That's a schematic diagram of a PFAS compound. And what we see are a bunch of F's and some lines and some O's, S's, and OH's. So those are elements linked together to create the chemical structure of a PFAS compound. So on the left in the oval, the red oval, is the fluorinated tail. So that's the long chain part of it. And you see a bunch of F's. Those are the fluorines. And then the lines cross. And in the middle of those lines would be a carbon. So the tail part is just a chain of fluorines and carbons. And those can be 4 carbons, so a C4 compound, and then 2 carbons each, all the way on up, C4, C6, C8, C10, C12, C14, and on and on. So if you read about these things in the literature, you might see that C4 or C8, those are the shorter chain PFAs. The longer chain PFAs like PFOS and PFOA, I believe, are C12s. And so I'm just giving you a little background on what that means. If you look at the chemical structure on the right in the blue oval, that's called the functional group. So it's a sulfur, some oxygens, and some hydroxides. And the way that that's arranged and the order of those elements determines what the acronym of the PFAS compound is. Next slide. And here's another diagram showing in a little more detail. The carbons are the black in the center, the fluorines in this schematic are green. The tail component is to the right in this figure, and it has a positive charge. And the head or functional group is on the left side, bottom left here, the red and the white, the hydrogen and the oxygen, and that has a negative charge. And so why these things are so persistent in the environment, why these chemicals stick around, is because the carbon-fluorine bonds are very strong and aren't easily broken at all. There's at this time, no known half-life for these chemicals in the environment. We do know that there is a half-life within the human body of, I believe, 2 to 9 years. So it doesn't degrade in the environment. But also what's interesting is because it has a positive side and a negative side, it is both hydrophobic and hydrophilic. So we find it at the interfaces of water and some other medium. So it'll be at the soil-water interface or at the water-air interface. Next slide. And this picture describes how that might look. So on the top, we have the air. The bottom and the bluish part is the water. The gray would be sediments. And basically, the PFAS compound in this schematic would be sort of facing head down with the hydrophilic, the water-loving head end of it, the negative end facing downward into the water, and then the long tail end of it, the fluorine carbon, out in the air portion. That's the hydrophobic portion, so it's away from the water, it doesn't like water. And so that's why we define these at these interfaces. And that's something interesting because in some of the studies I've read, it doesn't say where they sample specifically, but one would imagine that if you wanted to sample, you would want to do it at the surface of the water, or if you're going to go into groundwater, you'd find where the groundwater hits the soil interface. So I guess it's where the vadose zone meets the the less water-filled area of the sediments. So anyway, that's something to think about in terms of where you might sample. Next slide. As I said, these chemicals are very persistent in the environment. This is an image from the STEEP program at URI, the STEEP program, which looks to figure out the fate and the transport and environmental effects of PFAS. They have a very large grant from the federal government right now. But basically, the work that has been done to date shows that PFAS chemicals have gotten into our soil, they have gotten into our groundwater, and they're in our surface waters. And because they're in all 3 of those places, they're also in our drinking water. And so that poses a potential health risk for humans. In fact, the Harvard University study found when they looked at 94 different water supplies in 33 states, all of them had PFAS compounds in the water supplies. And that's water for 6.5 million people. And in all these locations, the PFAS compounds were above the federal guidance level of 70 parts per trillion. Next slide. So they're persistent in the environment. We do know now also that plants can suck up the PFAS from the water in the soil. And so that's both good and bad. It's good in that plants could potentially be a remediation technique, but it's bad because we eat plants. And at this time, when a lot of us are enjoying our gardens, it's something to think about. We think of homegrown food as natural and perhaps organic and free of pesticides and things. But if we have PFAS in our drinking water supply and we're watering with it, or if you have some legacy contaminants in the soil near where you live, you may have PFAS in the plants that you're growing for your food. Next slide. They're also persistent in the environment because these chemicals can both bioaccumulate and biomagnify. And what this image shows down below from the World Wildlife Foundation is how these two processes work. In the top part of the figure is a schematic describing bioaccumulation, which basically means that over the lifetime of an organism, when it's younger, it has a lower body burden or concentration of a chemical than it does when it's older. And that's because if it has repeated exposures to a chemical, it would tend to get more and more of a body load or body burden over time. And so that's what that's showing here with a schematic salmon. Low levels with a salmon smolt, higher levels with an intermediately aged salmon, and then with an adult aged salmon, very high levels. The bottom part of that figure is describing the process of biomagnification, which means that the concentration of a pollutant in an organism gets more concentrated as the organism is higher up on the food web. So in this picture, it's showing krill or shrimp then at the far end with very low contamination levels, salmon with slightly higher, elephant seal with higher, and then the polar bear, the top predator, having much higher levels or concentrations of the contaminant in its blood and in its tissues. So both these processes, bioaccumulation and biomagnification, help keep these chemicals in the environmental system. It's also in us, PFAS. A 2011-2012 Center for Disease Control study found PFAS in the blood of 97% of the Americans they studied. I can't remember how many folks were in that study, but you can look at it here. For all of these statements that I make that are numeric, I try to put a citation down at the bottom of the slide so you can look at it yourself. In the National Institute of Health and Environmental Health and Sciences put out this statement that PFAS exposure is difficult to assess, by which I understand them to mean that because there are so many different pathways through our soil, through our water, through our food, that we can get these PFAS in our system, it's really difficult to identify where, in fact, the actual source is that's getting into humans. This figure shows actual blood concentration levels of, I believe it's 1,000 women in Sweden. So the figure on the right shows the concentration on the left axis. On the bottom axis is time. And so the green line on the figure connects the concentrations over time, showing that concentrations in these women in Sweden were increasing in the early 2000s and then precipitously dropped after 2002, 2003, when PFOA and PFAS were discontinued. They're no longer being manufactured. And then the red line just shows the trend over time. So the good news is there's a significant drop in the concentration of PFOA and PFAS in humans over time. The bad news here is that there are thousands of new PFAS compounds. As I said, you can just take that functional group and change it a little bit and call the compound something else, and now use it on your coatings and your whatever else you're using it for. And we now need to start looking for those compounds in the environment and in human blood. Humans can become exposed to PFAS in a number of different ways, as I said, through the PFAS tainted food or water. The figure below shows counties within the US. This comes from Aquasana, which granted, it's a company that sells a filtering device, but it's referencing work that was done across the US, looking at a number of different water supplies, and the counties here in red contain water suppliers that have levels above the 70 parts per trillion guidance from the federal government. So it's widespread. You can see it's higher in some places than in others, but it's in our water supply. We can also become exposed as we apply different and use different products. For example, the Scotch Guard. If you're spraying Scotch Guard, you're probably inhaling some of the droplets. As you apply it to your rug or to your couch or to your clothing, there's probably some of that that's getting off onto your fingers and eventually into your food. Certainly we'd get into children crawling around. We can breathe it into the air, as I said, but also what we know most about the effects on humans in terms of these chemicals is from the folks who actually make it. So the first real signals that this might be a problem were for the folks, I believe it was in a DuPont, I can't remember, DuPont or a 3M manufacturing facility where they had really high levels of bad cholesterols. And it's because they were around these chemicals in the manufacturing, and that's one of the responses it has on the human body. Next slide.
Next. Sorry, froze up a little bit.
Okay. So why should we be concerned about this? Well, it's very widespread in humans. We can find it in human blood and urine. At this point, we don't know the full scope of effects of this class of compounds. It's in hundreds of different products, so we're exposed many different times. I know I use sticky notes. I'm certain I've been around waterproof products with waterproof boots and jackets, other coatings on fabric that I have in my house. So personally, I know I've been exposed many different times. When I made this talk back in April, I had a number of 4,700 PFAS chemicals that were registered. Since that time, Mark Cantwell from US EPA has told me that there are 7,000 registered chemicals. So there's quite a few to keep track of. And as we said, they're very persistent in the environment. And although an EPA circular says that they have a half-life of 2 to 9 years in humans, that's still a pretty long resident time. And so it's a lot of time for it to do whatever harmful effects it would have on humans. And lastly, it can bioaccumulate. So for those of us who, anyone who eats meat product, fish or cow or whatever, these things can bioaccumulate. And so if you're eating top predators, things like fish, they may have higher body burdens and be giving us PFAS that then accumulate in us. Next slide. So this slide lists a number of different things that have been found, I said, in part due to folks who work in manufacturing facilities, but there's some specific targeted things. PFAS do not kill people, so they're not acutely toxic, at least at the levels that we find in the environment. But what we do know is that it affects the thyroid, which alters our metabolism, slows down metabolism. We know it reduces fertility in women. It reduces fetal growth so that babies are smaller if they're exposed to mothers who have a higher body load of PFAS. In adult humans, it increases the risk of obesity, increases the level of bad cholesterol, it increases the risk of type 2 diabetes. So all of those are not good for longevity, obviously, increases heart risk because of those other two things, cholesterol and obesity. And it also reduces our ability to fight infections, which is something that's really important right now with COVID-19. So no, it's not toxic, but there are a number of lower level things that certainly would accumulate over time. And as well, we don't want our young folks to be born with lower birth weights and have the increased risks associated with that. Next slide. As you might imagine in the United States, because of this, there are now very clear connections between exposure to PFAS and these health risks and health outcomes, adverse outcomes. And so there's been legal ramifications, mostly in a couple of states where there are manufacturers. But Minnesota has been a really strong proponent of regulation of PFAS and research, the state of Minnesota, and recently won an $850 million settlement against the manufacturer 3M. Ohio, similarly, also has a class action lawsuit that has not been settled against 3M. And I just read last fall, maybe December, the North Alabama Water Authority won a settlement with 3M for $35 million to clean up a water supply that they had contaminated. And 3M and Wolverine Worldwide, which is a company that makes sneakers and hiking boots and outdoor clothing, have agreed to $55 million cleanup in the state of Michigan, and that was recently this year. So this is new, fairly new. You know, over the last 2-3 years, there's well over $1 billion worth of settlements, and I can imagine we're going to see a lot more, very similar to what happened with the cigarette industry and some other industries. Next slide. Closer to home. So I'm going to give 2 examples of places where there are cleanups near us here in Massachusetts. In the Pease Air Force Base in New Hampshire, just over the border, they found PFAS in the drinking water well at 2,000 parts per trillion, which is well above the 70 parts per trillion federal guidance and well above the 12 to 15 parts per trillion drinking water standard for the state of New Hampshire. They also found 50,000 parts per trillion in the aquifer beneath a fire training area on the site. So those are really, really high levels. It's an $8 million cleanup program. You can see that in the picture here, those are pipes carrying pumped water from underneath the former Air Force Base to a location where it will be pumped through resin beads that attract the PFAS through chemical attraction, and then the resin beads can be rinsed with salt water and the chemicals extracted. But then you still have the chemicals, and you put them in a container and you ship them off to someplace where they have to sit forever. So this is a pretty serious problem that we don't have a way to break these chemicals down at the moment. They're in drinking water. They're on vast tracts of land that are now not usable, and it's extremely expensive. Next slide. We have a colleague at CZM who lives in Hudson, commutes in from Hudson, Massachusetts. So she was very interested in this. You may have read it in the newspaper last year. The water supply for the town of Hudson violated the federal standard or the federal guidance of 70 parts per trillion. They found 76 parts per trillion PFAS in their drinking water well. And that's greater than the current 20 parts per trillion MassDEP drinking water standard. Why those PFAS are in their drinking water supplies? Because these 3 companies, Precision Coating, Boyd Coating, and Dillon LP, I believe were making coatings for ball bearings. And the waste from that activity is in the ground and got into the groundwater and is now in the drinking water supply for the folks in Hudson. Very similar to Pease Air Force Base, the remedy is you basically reverse pump, or you pump similar to like a drinking water well. You pump the water out, and then you have to send it through a series of resin bead matrices that then attract the PFAS, and you can extract them. This is now costing the small town of Hudson to have for a school or fire department or police department or paving roads or something. So again, it's a very expensive cost to clean these things up. Next slide. So what kind of research is being done in Massachusetts? For the next couple slides, we'll kind of summarize that. As I said before, at the University of Rhode Island, there's a program called STEEP, which is looking at the fate and transportation and ecological effects of PFAS compounds. They're focusing on Cape Cod. What we have here is a picture from their website that schematically shows a couple places of interest. Joint Base Cape Cod is an area where we know there are PFAS compounds because of the firefighting that was going on there. There's an Air Force base, there's a runway, there's a bunch of other things going on there too in terms of ordnance explosions. So definitely there were PFAS used there. The Barnstable County Fire Training Facility in Barnstable, there's an airport there, but also the fire training facility, so that's an area of interest. And you can see the airplane symbols. There's 2 other places on the Cape with airplane symbols. And several sites where they're very interested in looking at the compounds. So that's URI. Next slide. Folks who have done a couple of years of work on this issue, as well as other contaminants of emerging concern like pharmaceuticals and hormones, Silent Spring Institute and the Center for Coastal Studies out in Provincetown, with a MassBays grant, other work, I think they had a Mass Environmental Trust grant, has been sampling in estuaries along Cape Cod Bay, specifically for PFAS compounds They were looking for 16 different compounds, and they looked in 10 different tidal creeks. You can see them labeled here, from Old Harbor over in Sandwich all the way up to the Pamet River in Truro. And the next couple slides will show some of those results. Next slide. So this table, if we break it down, shows on the left side those 10 different locations in September and October. So Boat Meadow through Sissuit. They did it alphabetically, not geographically, so it might be a little confusing, but those are the locations on the left. Across the top are a select number of the PFAS compounds that were detected. Again, there were 16 different compounds, so this is only one part of their table presented that wouldn't fit on this slide. But what's of most interest is you look all the way, second column from the last, that's highlighted here in red, the sum of all PFAS. So that's one of the things that people look at. There are so many different compounds, and you can get one PFAS in a small amount and another in a small concentration. But really, we're interested in what all of them are together, because they all have similar effects on the body and the environment. So if you add them all up, here are the values you get, and these values are in parts per trillion. So the good news is they're all below the action levels at the federal level, the 70 parts per trillion. Some of them are above the drinking water level in Massachusetts, which is 20 parts per trillion. But we're not drinking this salt water. These are estuarine creek levels. But another pattern you will notice is that some places are higher than others. So Old Harbor has a slightly higher level. Rock Harbor, a pipe that they sampled there, has a higher level. And then the next slide, there's Namskakit, also has higher levels. Before we go to the next slide, if we go back, at the bottom of this slide, what is also interesting in the bottom red box is the detection frequency. So of all of the different times that they sampled, or different compounds that they sampled, here's the detection frequency. So these things are pretty widespread on Cape Cod, which is the point here. Also on this slide, you can see at the bottom, these authors, this is Laurel Scheider and Amy Costa. So Laurel Scheider is with the Silent Spring Institute. Amy Costa is with Center for Coastal Studies. The authors compared these data to other studies. And so you can see a rural coastal ecosystems and urban coastal systems levels at the bottom. And the highest levels found on the Cape were higher than the levels found outside of New York and New Jersey. So that's a very interesting point, because we think of Cape Cod as this pristine coastal area, and here it is having levels of PFAS contamination as high or higher as New York and New Jersey. Next slide. So that last slide was PFAS concentrations based upon grab samples that the researchers just put bottles in the estuary and took surface water samples. The data in this table is the results of passive samplers that were put out in the water column over a series of weeks and integrated the concentrations of PFAS. Basically, it's two rings of metal with a membrane in between them. And so the membrane attracts the PFAS, they attach to the membrane, and then you can get the chemicals off the membrane and figure out the concentrations over this time period. Again, looking all the way to the right, the sum of all PFASs, Nanskakit Harbor in the, I believe that's Orleans area, is very high. Also Old Harbor in Sandwich was very high, and Rock Harbor in the Brewster, Orleans area was very high. And so the authors have some thoughts on why these concentrations are so high. One of these locations is close to a septage facility, or a former septage facility that was recently discontinued in 2016. But obviously there's still some signal there from something. And so maybe it's a legacy contamination from septage being dumped into the watershed, not dumped, but being treated and discharged into the groundwater of the watershed. At another location, there is a potential wastewater discharge upstream from a religious facility. And at another facility, at another location, The Rock Harbor is in Sandwich. Sandwich is a town in which Joint Base Cape Cod has some property. There's some speculation that maybe that has something to do with the high levels there. But there's a lot of work to be done to figure out, why we have these higher concentrations in some locations than other. It's not presented here, and it wasn't presented in the published report or the written report by this group, but interestingly, near 2 of these hotspots, apparently there is a carpet company, which I'm just speculating, but I'm sure the carpet company sells a 3M Scotchgard type product that protects carpets. So it wouldn't be surprising then that the people adjacent to that carpet company would be using these products, and it would end up in their septic systems and then eventually end up in the watershed. But that would be something to track down also. And if you look all the way to the right, of the 14, so there were 16 PFAS they were looking at, 14 passed the QA QC test, and so they only report the results for 14. But of the 14, 11 to 14 were detected. So again, there's a lot of different PFAS compounds in the environment. We can find them. These levels are parts per trillion, so these are very, very small levels, but we know they're out there. And again, very small levels have human effects, which is why the drinking water levels are so low. Next slide. So in the next couple slides, I'll discuss a little bit about what's being done at the federal and state level to help folks out, to regulate these compounds and to address them. So in 2016, the U.S. Environmental Protection Agency issued what they call a health advisory. So this is not a drinking water standard. It's just an advisory level, some guidance about concentration of PFAS above which one would want to be concerned. And so that's the 70 parts per trillion number. The Federal Department of Health and Human Services put out a PFOA health advisory. So that's just a health advisory for one specific PFAS compound, of 78 parts per trillion for adults and 21 parts per trillion for a child. So that's in drinking water. In 2019, the EPA issued an action plan, which basically would evaluate the need, develop a true action plan, and develop cleanup recommendations. And then in 2020, there was the beginning of EPA's regulatory development process. So I put this slide in here because this frustrated me a little bit. So we've known about these compounds for years. We know their health effects, but our federal government over a 4-year period has only just started getting to the process of developing a regulation. So very similar to some other things that we're experiencing right now. It seems like the federal government is dragging its feet, and it's really up to state and local governments to establish rigid guidelines for drinking water supplies and for discharges. Next slide. Here's just a brief description of a few places that do have drinking water levels. In Massachusetts, the Massachusetts DEP just came out with a standard last year of 20 parts per trillion for several different PFAS compounds, either by themselves or as a sum, so all of them put together. So the level is, the concentration, the standard is the same for both individual and together, the sum of all, 20 parts per trillion. In New Hampshire, their drinking water level is 12 parts per trillion for PFOA and 15 parts per trillion for PFAS, for those 2 individual compounds. But that is under a court injunction right now, so it's not in effect. In Maine, they have a drinking water standard of 70 parts per trillion, and they have a groundwater standard of 400 parts per trillion. So that's pretty interesting. And in Massachusetts, we just have a drinking water standard. We do not have a groundwater standard. And a groundwater standard is obviously important if you're using that groundwater to water plants that you eat, things like corn and potatoes and other foods. So I imagine MassDEP might be moving towards that in the future. And in California, as in most things, they're a little more stringent than the rest of the country. They have a response standard for PFOA and PFAS, and then an even lower standard for their drinking water, what they call the notification standard of only 5 parts per trillion for PFOA and 6.5 parts per trillion for PFAS. So those are much lower than the 20 parts per trillion in Massachusetts. I'll also say, let me continue with this. That's fine. Next slide. So what this figure shows is, on the bottom is time access and different events that happened over time. The increments are not equal. So it goes from like 1991 to 2002, and then all the way to the right is 2020. Again, the increments are not equal. But on the left are drinking water advisory / guideline levels in concentrations. And what this picture is depicting is that in the late 90s, early 2000s, we didn't know as much about PFAS compounds. And so the guidance levels were pretty high, in the thousands to tens of thousands of parts per trillion. Very quickly, within 10 years, those numbers went down by a couple orders of magnitude. And we were talking about guidance levels on the order of hundreds of parts per trillion PFAS. And now we're in the sort of single to double digits, 3, 4, 10, 20 parts per trillion. So the science is evolving, and it's evolving in a way where we're determining that these things are having effects on humans and other animals at very low levels. And so the guidance is getting more and more stringent. And again, these are parts per trillion, nanograms per liter. So it's very, very small amounts. Next slide. Within the state of Massachusetts, our DEP is part of an interstate technology and regulatory council, which means they interact with other states, talking about methods, talking about the science, which is how Mark Smith from our MassDEP has come up with these levels of 20 parts per trillion. If you go to their webpage, I have the link here. There's a lot of good information about per and polyfluoroalkyl substances, PFAS, and you can see the picture from the webpage there. At the bottom is a picture of a popcorn bag. So many of us have heard the sort of urban rumor that microwave popcorn causes cancer. Well, this is why, because of the PFAS that are in the lining of the package, we know does have health effects. Next slide. What is interesting to me, as Jill said in the introduction, I work on the NPDES, National Pollutant Discharge Elimination System, discharges to coastal waters of Massachusetts. And in general, that's wastewater facilities, and there's just a couple of industrial facilities. But in the most recent NPDES permits, the discharge permits for the Newburyport, Rockport, and Manchester wastewater treatment facilities, MassDEP issued a statement about a page long discussing the importance of PFAS and urging wastewater treatment facility operators to voluntarily to be proactive and start to identify the sources of PFAS to their systems and to try to reduce them. And that was sort of, I'd say, a shot across the bow. I imagine the next few wastewater treatment facility discharge permits will start to have limits for PFAS. And so that's going to be a really big thing on the horizon, trying to identify sources and trying to eliminate them before they get into our surface waters. And so this diagram here just shows that there's so many different ways for them to get into our coastal waters. So the wastewater treatment facility, the manufacturing facilities, fire training facilities and airports, but also legacy contaminants from dumps. Many of the dumps have been capped in Massachusetts, but they're still leaking groundwater in some instances, and so those could contribute as well. And you see, just go back for a second. The cartoon in the bottom right shows a field, land application of biosolids. MWRA was giving away its biosolids, its pelletized sludge, as a fertilizer for a very long time, until they realized that there was PFAS in there and the levels were high enough that people probably shouldn't be putting it on the food that they eat, their lettuce and things like that. And so, that's a source to think about too. And if people had been applying it for a number of years to a field, one has to question whether or not those chemicals are still in that field, or, were they removed by extraction of eating the vegetables or what have you. Next slide. In the next couple of slides, we'll talk a little bit about, what can we do about this? So it's really well known because of the charges on the PFAS compounds that they attract to activated carbon. More so the longer chain ones. So when I was talking about the number of carbons, those are the longer chain ones. So C8, C10, C12, C14. The shorter chain ones apparently don't work as well, but they do still bind. The other thing that's been used, as in Hudson and the Pease Air Force Base, are these resin beads. So large containers, as you see below, these hoppers full of beads through which the water will pass, and then the resin, through chemical interactions, attracts the PFAS compounds and binds it and removes it from the water. Something that's still in research right now are things that are called nanoreactors that I don't know a lot about, but some chemists are trying to figure out how do we actually break the fluorine carbon bonds and break these things apart. And so that'll be something that's pretty interesting. But what's most important is, I believe, education and source reduction, for people to know what sort of products PFAS compounds are in, and just to start using less of them or stop using them at all. I mean, I personally have stopped using stain resistant things. We bought a couch recently. I was like, there's no way I want a stain resistant couch, having a child in the house. But there's other things to think about too. I'm not going to stop wearing a Gore-Tex jacket. It's a really important thing to have when you're out in the mountains or out in the water. So we just all need to think about how much of these things we need and how we can reduce them. Next slide. If you're at your home and you're concerned about the PFAS in your water supply, I did a little research, and just the type of pure granulated activated carbon filter that you can put on the end of your sink faucet in your kitchen. Those apparently work. I read a study, this model FM 2000B, adequately treated 100 gallons. You can go to the website there and check it out. I don't know how long it takes to use 100 gallons through the sink, but it did work very well with the PFAS compounds that were tested. If you were to use one of those water pitchers, like a pure water pitcher, and you put it in your fridge, they take out a small amount, but only 30 to 70% of the PFAS. But I guess that's better than nothing. And these granulated activated carbon systems have been tested by the Minnesota Department of Public Health. So you can go to their website and you can see which ones worked and how well they work. Next slide. So in summary, I know there's a lot of information. PFAS are chemicals that are used in non-stick or water repellent materials and fire retardant materials. They're persistent and ubiquitous in our environment. They're in animals, they're in plants, they're in us, they're in the soil, they're in our drinking water. We should be concerned about them because they produce chronic health effects. 20 parts per trillion is the drinking water level in Massachusetts. It's a little bit lower in New Hampshire and in California. And really, in my mind, PFAS are the next big thing. We talked about PAHs and PCBs for a long time. Many of us are working with nutrients on Cape Cod and other places, Buzzards Bay. But PFAS, this is a pretty big health issue, and you're going to be hearing about it for a while in your communities, especially since it costs so much to remove them. And the good news is that we can remove them with granulated activated carbon as a sort of low-cost way of removing.
Great, thank you so much, Todd. So as a watershed group, you may be wondering what you could possibly do about this, given how ubiquitous the contamination seems to be. But there's a lot of different things you could do, starting with education, informing your communities about the risk pathways that they may be exposed to, and providing information about the use of safer products. This website, pfascentral.org, is a wealth of information. I especially like this link that I'm showing a picture of on the right there. They have a list of recommended products that have low or no PFAS in them. And this is only covering a few of the categories like outdoor gear and car seats and shoes and things like that, but it goes into, home furnishings and many other categories. So this is a great resource for people that want to know what they can do starting today to reduce their risk. And as Todd said earlier, throughout this entire PowerPoint, we've tried to cite, almost every slide has a citation on it with a live link. So I'll make these slides available to you, and you can share them as much as you like and share those links as well. And of course, advocacy is a big part of the Watershed Group mission. You can advocate for testing and management at your community and your state level. research and staying current on the latest water standards, trends, and techniques, especially as this grows. And then monitoring, if it's interesting to you or if it's a goal of yours with your group, you can use targeted or passive sampling in the field. And that's what I'm going to talk about for the next couple of slides. The procedures for sampling for PFAS are really not outside your normal routine sampling that you're already doing. Many of the groups are doing bacteria sampling and other water quality parameters, and it's really very similar to that. So for surface water grabs, you're collecting a 1 liter near surface sample, and that's in HDPE plastic bottles, and just keeping it cold until it delivers to the lab. Passive sampling might be outside of the typical scope for many of you, but it's actually not that complicated either. So Center for Coastal Studies and Silent Spring use these polyethylene passive sampler tubes, which are really just sort of like a plastic bag material that you suspend out on some kind of mooring or anchor in the water column. And then the contaminants just adhere to the plastic, and then you can analyze the samples from there. They did have some problems using that method, and they did end up using the Polar Organic Chemical Integrative Samplers, the POCUS. That's the picture on the bottom right. So that's more of a canister that has membranes attached on the inside. Same idea as with the PE tubes. So the contaminants are adhering to the membrane, and then the membranes are then analyzed in the lab. So these passive techniques are deployed for several weeks, 30 to 40 days in the water column, and then they're collected. Sediment grabs, most groups have the equipment needed for this as well. Van Vliet grab, you just need the top couple of centimeters. And fish tissue, this is one of the more enjoyable ways of sampling in my mind. Electrofishing, netting, or angling, with or without the beer. And the goal is to look for both bottom feeders and predators. In the lab, samples need to be frozen or kept cold and shipped to lab, and then they undergo solid phase extraction, followed by liquid or gas chromatography, and a really fancy mass spectrometry. And then to get a feel for how much this costs, I got in touch with Alpha Analytical, and it really is cost prohibitive at this time. So Alpha Analytical can only quantify 24 unique compounds currently, and it's $275 per sample for surface water analysis, $300 for sediment, and $375 for fish tissue. So that's really expensive. If you're working on a small grant to keep your water quality program up and running, you know, this would chew through that money very quickly. So it's important to seek out partnerships if you're interested in doing this kind of work. There are groups out there that do want to partner and are looking for the type of free labor that watershed groups and volunteer-based groups can provide. This I'm just providing here so you have it as a reference. There's a really helpful QAP out there from Washington. They did a statewide study of PFAS throughout the state, and they did it in 2008 and repeated it again 8 years later. And if you're interested in developing any kind of survey technique, this would be a really helpful resource because they did it all. They did surface water, effluent sampling, fish tissue, and even osprey eggs, testing for 35 different compounds. And here are just some contact resources. If you were interested in starting up some kind of program, this is where you would want to start. You'd want to reach out to folks that are already working in the contaminants of emerging concern field. A lot of these folks are already working with each other. So it would go a long way to reach out with these people if you're at all interested in adding sites of concern in your watershed to work that they're already doing. Todd did mention that from Northeastern University in particular, Loretta Fernandez is especially interested in, she has a grant right now, and she's especially interested in finding samples and making those connections. And now I want to open it up both to hear the questions that you may have for Todd or for me, and also a question out to you all is if you've started hearing concern from your communities, from your residents about PFAS. Have they heard of them? Are they starting to ask questions of you? And do you see this anywhere on your horizon? So with that, feel free to unmute yourself. I will also check the chat box. I don't see anything there just yet.
Hi, this is Stephanie Murphy with Woods Hole Sea Grant. Can you hear
Hi.
me? Hi.
Yep.
I've been working with Christine Shreve from the Wellfleet Recycling Committee on a cooperative purchasing buyer's guide through the Care for Cape and the Islands project. And that's where I really began to get concerned about PFAS. We were looking for alternative products to plastic for restaurants when they provide takeout containers and to-go cups and things like that. And that's when we kind of learned that there are PFAS in the coatings of the molded fiber products that people often use for takeout, and also in the linings of hot drink cups, like every Starbucks cup has a PFAS lining. And so we're looking for alternatives to those. But I just wonder, I guess my question is, how do you know when something has PFAS? Like, I always looked at those molded fiber products as like, oh, isn't that great? This is a nice alternative to plastic. And, it took some research on our part, or just some digging. And I don't get a lot of questions like this in my organization. And I don't hear a lot of people talking about it to sort of answer your first question there. But it seems like information is a little bit hard to come by. And Todd, you mentioned the dental floss, and like, how do people know when there are PFAS in products like that?
This is Todd. Hi. Jill, I think on one of your slides, you have the website of the PFAS, I forgot what it's called, but there's a website that has a whole lot of information. And I think they have, products that have PFAS in them, and then PFAS-free products. That's the only thing I know of. I haven't seen a lot, honestly.
Yeah.
And I think that one of the problems is there's, over 7,000 compounds in hundreds of products, and we just don't know about them. And I think a lot of this is unfortunately gonna have to be big government saying, hey, these things are not good, take them out.
Right.
Because
sorry, go ahead.
I was gonna say, just because they are really useful. As you said, things slide off of them, they make things work better, but we don't want them.
No. Yeah.
Yeah,
Okay.
I read somewhere that if a material is stain resistant or waterproof, it most likely has PFAS in it. It might not be one of the compounds that's on our radar yet, or anyone's radar yet, but it most likely has a concerning compound in it.
Yeah. In our research, we found products that were touted as, green alternatives, and they had some proprietary coating on there, which it makes it really hard to figure out if there's PFAS in there or not. So, we were kind of stumped in some cases as to whether we could actually recommend something or not.
Yeah, that's good information. I think, well, I said that part of this is probably going to be big government telling us, regulating things at a higher level. But I think it's also, groups like you finding these things out and bringing it to our attention. I wouldn't have thought that a fiber product takeout container would have PFAS on it, and certainly wouldn't want that. I wouldn't want to take my daughter's food home, or, the spaghetti in the thing that's covered with PFAS. No.
Absolutely.
I will add, if you don't mind going to that last slide again or second to last slide with the folks' names on it. I talked to Mark Cantwell from US EPA, EPA Office of Research and Development. I asked him about, if somebody wanted to do this type of work, as Jill pointed out, it's very expensive. So he very strongly recommended that anyone should contact these groups. Laurel Scheider worked with Center for Coastal Studies, and I think in part that was because Amy Costa has a really good monitoring program already. They have a boat, you know, they have equipment, they know the water. So for any of you who have a program and you have some of that capacity, I think that helps a researcher out. So the researcher's got the lab, he or she has the equipment, they have the grant, but I think it would be really useful if they also had, you know, hands in the water, if they had local knowledge, if they had a boat to get out to someplace, folks who would give them some direction to sample and help them build a good story. Like, hey, we're very concerned about this location because A, B, and C. And I contacted Loretta, and she seemed very interested in working with the group. And the URI STEEP program, you know, they're not working in Rhode Island. They're actually working in Massachusetts Bay. They're working in Massachusetts. So there's an opportunity to, even if someone has an ongoing program, give them a call and say, hey, what do you think about sampling over here? That might be, you know, for this reason.
Yeah, that's great. Well, we're past the 3 o'clock hour now, so without any other questions, we'll end the talk here. But I'm going to make the video recording available on our YouTube page, and the PowerPoint will be available to everyone as well. I'll email that out. But feel free to contact Todd or I with any questions that might pop up. And I guess stay safe and PFAS free.
Thank you.
Thank you very much, Todd.
Thank you. See you everybody later.